All right, let's jump right into this. Think about our modern electrical grid as a massive, living organism. If the transmission lines are the veins and arteries carrying energy around, then the transformer, well, that is absolutely the heart of the whole system. And just like a vital organ, these things are incredibly expensive, super hard to replace, and literally indispensable. Because of that, you can't just plug these giant machines in, walk away, and hope for the best. No way. You have to surround them with an elite squad of highly specialized bodyguards. So today, we're breaking down exactly how that works in the Transformer Protection Threat Matrix.
Okay, let's dive into this. Here is our structural threat matrix for today. We'll cover the need for protection, thermal threats, electrical shields, oil and gas defenses, and lastly, pressure and flux controls. Starting with Section 1. The need for protection, the VIP bodyguards.
So why do we go to such extraordinary lengths to protect these assets? Well, it really depends on the size of the VIP. For a smaller unit, say under 500 kVA, simple fuses might actually do the trick. But once you cross that 1000 kVA mark, you absolutely require heavy-duty circuit breakers and intelligent relays. And there are 3 core reasons for this. First, they're immensely costly. A failure is a massive financial hit. Second, they do the fundamental heavy lifting for the grid, stepping voltage up for transmission and stepping it down for distribution. But the third point is the real kicker. Protecting the transformer means you are protecting every single piece of connected equipment downstream. If a transformer fails catastrophically, it can send a dangerous surge cascading all the way down the line. It's a domino effect we definitely want to avoid.
Now, before we look at the specific threats, I want to drop a quick insider tip for anyone looking to get into this field. Memorize this right now. 50 and 51. The 5051 code is the universal industry designation for overcurrent protection. If you're ever sitting in an interview for a junior electrical engineering role, I promise you this is a guaranteed question. Know that code and you'll instantly sound like an industry veteran.
Moving right along to Section 2, Thermal Threats, OTI and WTI. As a transformer takes on electrical load, it generates heat. And heat is the absolute ultimate enemy of its lifespan. If you let it run uncontrolled, it'll literally degrade the insulation right inside the unit. We monitor this using 2 main indicators, OTI for the oil and WTI for the winding. Now, what's really interesting about this slide is the visual contrast in those numbers. The oil triggers an alarm at 80 degrees Celsius and physically trips the breaker at 90. But look at the winding. The alarm is at 85 and it trips at 95. Why the difference? Because the electrical windings are where that heat is actually being generated in the first place. They are naturally always going to run about 5 degrees hotter than the cooling oil surrounding them. And here is just a brilliant little piece of mechanical engineering for you. During routine maintenance, field technicians don't have to somehow boil the entire transformer to test if the system works. They can just physically open the gauge cover and manually push the temperature needle up with their finger. When it crosses those thresholds, it immediately verifies that the relays are actively talking to the breaker. Boom, test complete.
All right, Section 3, Electrical Shields, Overcurrent, REF, and Differential.
Transitioning from those slow-building thermal threats, we're now looking at split-second direct electrical threats. Remember that 5051 overcurrent code we talked about? These relays are your absolutely fastest responders. Here are the main culprits they're looking out for. Short circuits, maybe an incorrect system design that's pushing way too much load, sudden arc faults, or ground faults. When any of these happen, the current spikes dangerously fast. To fine-tune exactly when and how fast that breaker needs to trip, engineers have to carefully set the plug setting multiplier, the PSM, and the time multiplier setting, the TMS. It's all about precision protection.
But sometimes you need hyper-focused precision. And that's exactly where REF comes in. Restricted Earth Fault Protection. This guy strictly guards the star point or the neutral area of a star-connected winding, and it is incredibly sensitive, triggering at just 1 to 3% of rated current. So you might be wondering, how does it not just trip all the time? Well, it's because of that restricted zone. Any external fault outside the transformer essentially cancels out in the neutral CT. But the very millisecond there's an internal fault inside that specific restricted zone, the balance breaks and it trips instantly. No hesitation. Which brings us to the big guns. Now, you might use some of these protections on a 2 MVA transformer, but 5 MVA, that is the universally recognized critical threshold. Once your transformer hits 5 MVA and above, you are mandated to deploy the absolute ultimate electrical shield, differential protection.
The basic physics behind differential protection are honestly beautifully simple. Think of it like a giant electrical scale. The current entering the transformer zone should perfectly equal the current leaving the zone, assuming you account for the turn ratio. The relays are constantly sitting there, comparing the primary side with the secondary side. If those numbers don't match up, it means current is leaking or shorting somewhere inside the transformer itself. Any unbalance inside that zone equals an immediate trip.
But this introduces a pretty massive engineering problem, and it leads to a classic high-yield interview question to really test your understanding. So why is a restraining coil required in differential protection? If you just have simple differential monitoring, you actually have a critical flaw. Any guesses?
The answer is all about the startup phase. When you first energize a massive transformer, there is a sudden temporary surge of magnetizing current called inrush current. It's a completely normal, totally harmless part of the physics, but to a basic differential relay, it looks exactly like a massive internal fault. The restraining coil is this brilliant, game-changing addition designed specifically to absorb those harmless inrush currents. It prevents unnecessary nuisance tripping from shutting down your entire grid every single time you try to turn it on.
Okay, Section 4. Oil and gas defenses, the Buchholz relay, and MOLG.
Stepping into the physical mechanics now, these are absolutely critical for oil-filled transformers above 500 kVA. And the undisputed star of the show here is the Buchholz relay. For any field technicians out there, I want you to build an accurate mental map of this hardware. The Buchholz relay is physically mounted right on the connecting pipe between the main tank, which holds the core, and the conservator tank sitting up top. Its exact physical location is the key to how it does its job.
And it operates in two perfectly escalating steps. Let's say there's a minor internal fault. It slowly burns the oil, creating these little gas bubbles that naturally float up the pipe and right into the Buchholz relay. This slow gas accumulation gently lowers a float hinge inside, triggering an alarm. But if there's a massive, violent short circuit, the extreme heat creates a fast, forceful surge of oil straight up that pipe. That physical wave of oil violently throws a second hinge, instantly sending a hard trip signal to the breaker. It escalates beautifully, based entirely on severity.
Working right alongside that is the MOLG, the magnetic oil level gauge. This guy sits right up on the conservator tank and acts as your early warning system. If your oil level starts dropping because of a leak, the MOLG is going to tell you. And trust me, you literally cannot ignore this. Because if you let that oil level drop far enough, air is going to enter the Buchholz relay, it'll drop that float hinge, and it's going to shut down your entire transformer anyway.
Finally, Section 5, Pressure and Flux Controls, the last line of defense.
These are your extreme physical failsafes, the last thing standing before the transformer literally destroys itself. First up is the PRV, the pressure relief valve. When really serious faults happen, the oil inside vaporizes instantly. That creates crazy, dangerous internal pressure inside a sealed metal tank. If that pressure has nowhere to go, the tank ruptures. The PRV is basically a heavy, spring-loaded safety lid that automatically pops open at a set limit to safely release that explosive pressure. So the crucial point is this: if a PRV pops, it means something violently went wrong. You never ever just reset it. You absolutely must investigate why that pressure spiked in the first place.
And our final specialized defense is overfluxing protection. Transformers rely on maintaining a very specific magnetic flux in their core. If you suddenly get high voltage transients on the line or a drop in frequency, the volts per hertz ratio spikes. The mutual flux increases rapidly, and that generates severe, damaging heat right inside the iron core. This specific relay acts incredibly quickly to monitor that balance, making sure the volts per hertz ratio stays safely locked right around 1.05.
So we've covered a massive matrix of defenses today. Everything from simple temperature gauges to hypersensitive differential zones and heavy-duty pressure valves. But I want to leave you with one final provocative thought here. Let's say your PRV pops or your Buchholz relay trips, and it successfully physically saves that multi-million-dollar hardware from destroying itself today. What is the critical hidden threat you have to find next? The relay did its job perfectly, but the true engineering job, your job, is figuring out the root cause of that fault so you can save the system again tomorrow. Thanks for diving into this with me.